Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 15, 2026, which was about 3 days ago. It delivers a sobering result for mechanistic interpretability, finding that sparse autoencoders recover only 9% of true features in synthetic setups despite high explained variance, and they barely outperform random baselines on real downstream tasks. The paper is titled, Sanity Checks for Sparse Autoencoders Do SAES Beat Random Baselines? And, as we'll see later, these results raise serious questions about whether we are truly finding meaningful patterns inside neural networks. Figure 1 illustrates the experimental design and the surprising results. On the left, the diagrams show 3 control setups: a frozen decoder with fixed random outputs, a soft frozen decoder that allows only minimal updates, and a frozen encoder with fixed detection patterns. On the right, the bar chart compares these against a fully trained sparse autoencoder. Surprisingly, the soft frozen baseline in dark blue performs nearly as well as the fully trained model in gray on metrics like automated interpretability. This suggests that high scores on these benchmarks might not indicate meaningful feature learning. Well, Figure 2 dives into the synthetic results using the constant probability setting, which is the simplest test case where every feature appears equally often. These histograms plot the cosine similarity between the ground truth features and the closest feature found by the autoencoder. On the left, we see the batch top K model, and on the right, the jump re-LU model. Crucially, even though both models achieve a solid explained variance of 0.67, the distributions show they fail to recover the true features. Most scores cluster near 0.4, right around the red dashed line representing random initialization, meaning the models are reconstructing the data without finding the underlying truth. Next, Figure 3 shifts to the variable probability setting, which is a more realistic scenario where feature frequency varies wildly. The vertical axis plots this frequency on a log scale, and the horizontal axis shows how well each feature was recovered. A small cluster appears in the top right dashed box, indicating that the models successfully learn only the most frequent, high-activity features. In contrast, the dense vertical band on the left reveals that the vast majority of rarer features are ignored, scoring no better than the red random baseline, even though the total explained variance is quite high at 0.71. So, Figure 5 moves to real model activations, evaluating them with automated interpretability scores. The charts display distributions for batch top K models on the left in blue and jump re-LU models on the right in red. What stands out is how closely the soft frozen decoder, shown in the third column of each plot, matches the fully trained model in the first column. For instance, in the blue chart, the fully trained model averages 0.90, while the soft frozen version reaches 0.87. This suggests that high interpretability scores can appear even when the model's features are constrained to remain near random initialization. Alright, Figure 8 examines causal editing using the RA versus EL benchmark, which tests if modifying a feature predictably changes the model's output. The charts display batch top K models on the left and jump re-LU on the right. Crucially, the soft frozen decoder, marked by squares, matches the fully trained model shown with triangles across all sparsity levels. This finding is significant because it suggests that successful causal editing does not prove the model has learned true features, since a semi-random baseline achieves the exact same control. Finally, Table 1 contextualizes these results within the broader debate. The left column lists the claimed benefits that drive enthusiasm for this technology, such as the promise of monosemanticity, where features correspond to single concepts, and scalability to frontier models like GPT-4. In stark contrast, the right column outlines the documented limitations that this paper reinforces. These include the tendency to find spurious features, even in random networks, poor generalization across tasks, and training fragility. This comparison underscores why simple metrics like reconstruction quality are no longer sufficient proof of success. Wrapping up, the main takeaway is stark. If a model initialized with random noise performs nearly as well as a fully trained one, our current evaluation metrics are likely broken. The authors urge the community to adopt these frozen baselines as standard sanity checks to ensure we are not just chasing statistical ghosts. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.